I would like to first thank the organizers for giving me this opportunity to present our work here. So today I'd talk about multi-wavelength line intensity mapping and how you can do cosmology with it. And I will start with pretty early phase of the universe, and eventually we will come closer to the present day. So the first phase that I will talk about, the cosmic phase, is the epoch of reionization, which is essentially the period when the first sources of lights like galaxies, quasars, and first formed, and they gradually ionized and heated the intergalactic medium. Obviously, it would be great to see the IGM as well as these sources all together with highest resolution and details possible, but that's not necessarily the case. Even with JWST or ALMA, probably you will be able to see only the sources which are extremely bright in this particular period. However, as we all know, more or less, the belief is that the faintest galaxies are the ones which are numerous and probably has driven the reionization most of the cases or models, let us say. So the challenge is how to observe those galaxies or their impact or those sources' impact on the reionization. So essentially there comes this unique technique which has been in the field for quite some time, and it is being used particularly for observing the IGM, particularly using 21 centimeter line. However, for the sources, this is slightly new compared to the IGM observations, and that is using unique line emissions from the galaxies. Essentially, you can probe these galaxies. And how do you do that? Even for a faint galaxy, if you make a big pixel or voxel and add up all the emission from of a particular line being emitted by a bunch of galaxies that are lying within that voxel and paint that voxel with that integrated flux, essentially you get a bright cell or a empty cell, essentially. So using this, you can make a coarse-grained image of the sky of that particular line that you are targeting. So now if you choose your lines judiciously, that line might be associated with the star formation rate, etc., and might help you to understand whether that type of galaxies were, means the lines emitted, what kind of galaxies were dominant at what time. Essentially, you can forward model this process and do the all your interpretation. So essentially the idea is that the large scale structure is galaxies are the biased probes of large scale structure. You are unable to detect individual galaxies at high rate shifts or the faint galaxies. So you make a coarse grained image using line intensity mapping. Now you can choose various kinds of lines, and depending on your instrument, if it is concerto, you target the single ionized carbon. If it is COMAP, you target CO, redshifted CO line, and if it is SphereX, which is launched a few months ago, essentially which targets various kinds of Lyman alpha and other lines. And for IGM, then you can target the neutral hydrogen 21 centimeter line. And effectively the maps that you will get out of it would be something like this. This will how the sources look like, and this is how the ionized IGM or ionized and neutral IGM would look like. And once you have those observations, you would like to interpret them. To interpret them, you need to build forward models, and these forward models will involve simulating the large scale structure and then painting these halos with particular line emission, depending on the star formation rate in those halos, depending on the model of star formation that you choose. Similarly, you can post-process the dark matter density field and the sources and produce a H1 map as well, 21 centimeter map as well. So one former PhD student at IIT Indo, Chandrasekhar, along with me and Kanan Datta here, has done a bunch of work on this particular domain, where he essentially developed a tool to simulate both the C2, CO, and 21 centimeter line from the epoch of reionization. So the first work that he focused on essentially was what is the impact of the light cone effect? What is light cone effect? It is essentially the evolution of the signal along the redshift axis or along your line of sight. Now, when we interpret these observations, we may or may not include this particular effect. The signal evolves along the cosmic time, right? So the evolution is more or drastic in case of the IGM signal, whereas the source signal, this line intensity map, you don't see that much evolution because structures basically evolve rather slow compared to the state of the IGM. So what if you include this particular fact in your forward model and you don't include, and what happens to your interpretation? So we looked at something called the cross power spectrum of C2 and 21 centimeter signal, and by including this particular effect inherently in our simulations as well as not including it, and if you do not include it, the change in your interpretation becomes more than 20% or so in sufficiently large scale. It depends on the history of reionization as well. If your reionization is fast or slow, that actually tells you whether this light cone effect will be significant or not. So it's better to include it for interpreting your signal. That was the more or less conclusion. Now there is something when you are doing this forward model that we generally ignore, not always, but generally ignore, is that there is a line luminosity halo mass relationship, and this is more or less an empirical relationship people use. Now, while using this empirical relationship, people do not take into account the astrophysical scatter that might be there in that line luminosity halo mass relationship. Now, this astrophysical scatter may depend on depending on the environment of the that galaxy that from which this line is being emitted. So we picked up some hydrodynamical radiative transfer simulation, SIMBA, and which was processed by a chemistry code called SIGAME by a group in Copenhagen. So, and we looked at this line luminosity and halo mass relationship that they had published. So, and you can see there is a significant scatter. Now, if we include this scatter, this arises due to this multi-phase state of the ISM. If we include this scatter in our forward model, how do we include it? First question, and then whether that has an implication in your interpretation or not. So we started basically trying to fit this scatter using various kinds of approach. One is with the mean, one is with the essentially the most probable fit, etc. But nevertheless, the most important outcome is that when you look at the auto power spectrum of the C2 signal, if you do not include the scatter, then essentially you are either underestimating your signal by more than 200% or sometimes 250% or so, depending on the scale. So, and depending on the model of the scatter that you implement. So, one should take into account this particular scatter. Next thing is, once you think about the scatter in the source model, how does that source model scatter affect the IGM signals? So, people have worked out a bit on this as well, and where they have actually looked into the ionization field's power spectrum and impact of the scatter on that ionization field power spectrum, and they kind of reported that there is no significant effect essentially. However, Kanan Dutta here, he proposed maybe this scatter introduces some sort of non-Gaussianity, additional non-Gaussianity in the signal, and power spectrum is a two-point correlation function, would not be able to detect that non-Gaussianity. So maybe we should look at higher order statistics after including this particular scatter in our signal. So we did the same. We actually modeled included a log normal scatter in this line luminosity and halo mass relationship into our simulations and generated many realizations, essentially 300 such realizations, and looked at something called bispectrum. First of all, we looked at the power spectrum and we didn't see much of an effect. There is 10% or so effect at some scales, but not much, which is kind of in agreement with the previous work. Whereas when we looked at the bispectrum, essentially the effect was quite significant, but whether this effect was just by chance, just statistical fluctuation or not, to test that we also did a statistical significance test where essentially we calculated the ensemble average of the sigma of that change, that's impact due to that scatter. And we set the criteria where the impact, the statistical significance is more than 3 sigma, we will consider that as a significant effect. And it turns out that it affects the small scale bispectrum, that is large K mode bispectrum, where the statistical significance is high as well as the impact is also high. And this is simply because of the fact that in different realization, the small scale bubbles, actually small scale ionized regions vary from realization to realization. That's why this effect is significant at small scale, but not at large scale. Now, we also looked at a scenario where essentially we modeled this CO instead of C2, now CO luminosity halo mass relationship, and we made this luminosity pretty low, extremely weak, so weak that it is not detectable using any of, let's say, the COMAP surveys at 3 sigma level, at least at certain parameters, for certain parameters of this model. But when we started looking at the cross power spectrum instead of auto power spectrum of CO, we started to pick up this extremely weak signal. So cross power spectrum actually helps you to pick up the extremely weak signal that is not detectable via the auto power spectrum. There are other reasons why you would do cross correlation, but this is one of them. Now, moving into the post-reionization era, essentially we ask the question, okay, what happens at this phase? So at this phase, essentially the 21 centimeter signal as well as your C2CO and other line intensity maps will come from the same sources, the galaxies, right? So if I want to know how the matter has clustered on the basis of galaxy survey or on the basis of intensity map, what I will actually gain if I choose galaxy surveys. The problem with galaxy surveys again is that you miss out on the faint galaxies, so your interpretation will be extremely biased. On the other hand, if you choose these line intensity maps to do in post-EOR, probably you get a better constraint on your baryon bias essentially. So that's the question we try to address. However, what instrument you do, and we chose SK simply because of the fact, if you look at the documentation of SK in the phase 2, there is a proposition of adding a high frequency feed. So you can in principle observe both 21 centimeter and CO 10 transition line intensity maps using SK phase 2, SK mid essentially simultaneously in these overlapping redshifts. So there is a range of redshifts which kind of overlaps. So the first question is that whether these redshifts, at these redshifts things will be detectable or not, and this particular work is led by this particular student, Mohit, and so we essentially simulated again in the same fashion the 21 centimeter signal. Now the 21 centimeter signal comes from the galaxies, and the CO signal from the galaxies as well, following the same formalism. But this case we used illustrious TNG simulation, so which actually gives you the H1 mass by default, and also you have the star formation rate density. So from the star formation rate density, then we painted the halos with CO luminosity. Now, once you have simulated these two things, you then ask the question what statistics to use. So far I have talked about Fourier statistics, 2-point or 3-point correlation functions in Fourier domain. However, you miss out if you do those kind of statistics on the fact that the phase information is completely lost, because it is some sort of an average that you get. So to obtain the phase information, you need to do some sort of morphological analysis. So if you can make these coarse gridded maps of the universe using these line intensity maps, probably you should first try at least the morphological analysis on those maps. So whether those maps are possible to make or not, to check that we actually calculated the SNR for the 21 centimeter as well as for the CO. Now for the 21 centimeter, the situation is pretty grim. You need at least 5,000 hours of observation to get a 1 sigma detection at around redshift 1.4 or so. However, for CO using SK2 mid, just for 100 hours of observation, you can actually get a significant amount of SNR, more than 3 definitely. So we chose this particular redshift which kind of overlaps between 21 centimeter and CO emissions using the same instrument. And we applied 2 different morphological statistics. One is basically percolation transition statistics, which is determined by something called largest cluster statistics. So this has been applied in galaxy redshift survey extensively. What you do essentially, you ask the question, if there is a galaxy or a bright cell and all the neighboring cells are around it, how quickly this bright cell gets connected to other bright cells in how many quick iterations. By quick iterations, I mean you paint all the neighboring cells of a bright cell as bright and then do this map and then ask the question, are they connected with each other? If not, you do another round of painting for all of the bright cells, because now you have more bright cells, and eventually after a number of iterations, all of your cells gets interconnected. That means the structure has percolated. So that is the percolation transition. You can quantify this by something called LCS, largest cluster statistics, which is essentially volume of the largest cluster at any given time, any given iteration in this case, divided by the total cluster volume. Now, and you can calculate also something called filling factor. Filling factor is nothing but how many cells are bright divided by the total number of cells in your survey volume. So if you plot it and you see this sudden transition in largest cluster statistics at a specific value of filling factor, that actually tells you that the structure has percolated. So how many iterations do you need to get this percolation? That's the question we asked, and it turns out that more or less, for whether it is galaxy density or 21 centimeter brightness temperature, they more or less percolate almost at the same filling factor, whereas the CO is a bit later. The percolation happens a bit later. So to verify whether this statistic is at all, the results are at all reasonable or not, we chose another statistics which is called local dimension, which actually tells you whether the cluster of points, whether they are line, sheet or clusters, the cluster of points that you are looking at, and by calculating the local dimension, nothing else. So this dimension D is 1 for line, D is 2 for a sheet, and D is 3 for a sphere or a cluster or node. So we applied this on our galaxy density maps, our 21 centimeter maps and CO maps, and as you can see, the galaxy density and 21 centimeter maps more or less show something between a sheet and a cluster. So from 2 to 3, something in between that. Whereas the CO shows more or less same thing, but there is something slightly more weightage towards the sheet-like structure. So to verify whether this is at all detectable in an actual observation with SK or not, we essentially simulated the SK like noise and injected it in our 21 centimeter maps first, and first of all, if you don't do any kind of denoising, you don't get anything about this related to this particular statistics. So you have to do basically some sort of a smoothing of your images by to do some amount of denoising, and if you keep on increasing your smoothing radius, essentially you start eventually to pick up the same sort of structure in your probability density function of local dimension. Whereas and that can be done only for 5,000 hours of SK observation, which is unfeasible, I think. However, if you are looking at the CO, then only 1,000 hours of SK observation, and without any denoising, just by setting a 3 sigma threshold based on the sigma of your noise that you have in your observation, you can start recovering the actual true signal morphology. And so the question that remains is that why we see slightly different morphology in case of CO and in case of 21 centimeter, because probably because the star formation rate might have quenched preferentially at higher local dimension, and probably it peaks at sheet-like structure. So with this I will stop here, and probably CO will be detectable. If you use CO, you can probably do this morphological analysis using SK, but probably not with 21 centimeter. Yeah, I will stop here.
Thanks, Suman. Now we have time for a couple of questions.
Yes, so this light cone effect, is this coming because your voxels have a finite size? So
the voxels are small, but when you are calculating any statistics, you are taking a chunk of your observation along the line of sight. So how much chunk you choose, depending on that, the evolution, that much evolution you are in.
the voxel along the line of sight
Exactly.
is long enough so that things evolve.
Yeah.
So the velocities don't affect the peculiar velocity.
So peculiar velocities are already included in this analysis. So this is with redshift phase distortion. Yeah.
For the 21 centimeter cross correlation with C2, do you need to worry about extragalactic point source foreground in the 21 centimeter?
Yes, you do, because if you, okay, in principle, the foreground for these two observations are different. One of the basically point of doing cross correlation is that because they are systematically different, if you cross correlate them, they might cancel out. But that is not completely true. It will impact your sigma, your variance of that particular estimator. So it is going to affect in some way. So some sort of point source removal is required. Otherwise, it will be problematic.
Is there a possibility of the point sources that are contributing 21 centimeter foreground or can also be contributing to C2 signal?
There might be a possibility, though the frequency difference, the frequencies that these two observing frequencies of these two lines will be vastly different, but there is a possibility that might affect.
Thank you.
Yeah.
So I have a naive question. This is related to assigning CO to a low luminosity objects.
Yes.
Because you are saying that intensity mapping is a powerful tool to look at the low luminosity
Luminosity
objects.
objects, yes.
That is true for H1 because H1 will follow at some level dark matter.
Right.
Whereas here there are two nonlinear effects. One is that metallicity dependence on the luminosity or whatever you call mass. The second thing is that ISM fraction.
Exactly.
CNM fraction may be very low there.
Exactly.
So what will be the effect of actually including something like a chemical analysis in this? Because Simba and all, they do it, but they don't reach the kind of masses you would like to see in your distance.
I agree. So I think that particular part of the analysis is still unexplored, mostly. One of the major reason is that obviously to do this chemical analysis at those low mass objects, first of all, you don't resolve them always. And even though you resolve them, then you don't have a large enough volume to make these kind of survey simulations, etc. So I think it depends obviously on the model and it is something needs to be explored. It has not been explored properly. I don't think so. Yeah.
Hi, thanks for the nice talk. I have a question, naive question. For the CO signal, how well can we theoretically model the total intensity instead of the power spectrum?
This is very naive model, whatever I have showed. So because it's just painting the luminosity of the CO based on the star formation rate in the galaxy.
Assuming this model, what will be the uncertainty in the intensity? There must be some theoretical predictions, right?
Right. So there are basically you can effectively play with these two parameters. I didn't discuss it at all, but yeah. So let's say there are these two parameters, this alpha and beta, which are again parameters of a scaling relation obtained from the local universe observations, individual galaxies. So we don't know well whether these relationships are at all valid at the high redshift or not. That also has not been verified. So it's pretty unexplored domain.
Thank you very much. Thanks.
So thanks, Suman.